Welcome to week 12. The problem of the week is going to be discussing integrating factors. It's entitled Making a Total Derivative and then Solving Differential Equations the Easy Way. So integrating factors are one of the hardest things that one has to figure out if one's trying to solve a nonlinear equation that is reducible to an exact differential equation. So just to remind you, our first order nonlinear differential equation can be written as dy dt equals minus m of ty divided by n of ty, where m of ty and n of ty are functions. In this case, they're arbitrary general functions of both t and y. And because the dependence that they have on y is not necessarily linear, that's why this becomes a nonlinear equation. Now, we've discussed this before, but you can immediately see that if I took m and n and multiplied it by any function q of t and y, the differential equation doesn't change because that factor q of t and y cancels when I calculate the ratio of m over n, and this means that there is a non-uniqueness in the choice of m's and n's. And so you can be presented with a differential equation that if you found a different representation by choosing an appropriate q of t and y to multiply the equation by, then that modified equation, which is the exact same solution as the original equation, might be easier to solve. And that's the whole notion behind something that's a reducible equation. We're going to be modifying the differential equation into something that we already know how to solve. So if I re-express that differential equation, it becomes m of ty dt plus n of ty dy is equal to 0. And we want that to be a total derivative. And for that to be a total derivative, the m of ty has to be a df of t and y by dt, and the n has to be a df by dy. And because the mixed derivatives are equal, that means if I take m and take its derivative with respect to y, that must equal the derivative of n with respect to t. So this equation is the consistency equation for a nonlinear differential equation to be solvable by the exact differential or exact derivative technique. So that's the goal that we have, is can we find a q factor that will guarantee that the ratio of these derivatives of the m with respect to y and the n with respect to t are equal to each other. So we're going to assume that the m and n actually don't solve it, but by multiplying with a q, we can get them to solve that relation. And so let's just plug in what the derivative of qm with respect to y is and what the derivative of qn with respect to t is. Then we get dq dy, we just use the chain rule, dq dy times m plus q dm dy equals dq dt times n plus q times dn dt. And the goal is, can I find a q of ty that satisfies this equation? Now, this equation in general is not easy to solve. It ends up being a partial differential equation. We haven't really even talked about partial differential equations. But it turns out that if the factor that we need for the integrating factor is just a factor of t, or it's just a factor of y, then these equations do simplify, and we can immediately find the integrating factors. And that's the situation that I'm going to be discussing for you today in this problem of the week. We're going to show exactly how you do that for each case, starting with the case where q is just a function of t. So if q is just a function of t, then dq dy is equal to 0. And I can rewrite that equation that I have to satisfy as q times dm dy plus dq dt n plus q of t dn dt, is equal to dq dt n plus q of t dn dt. Now what I'm going to do is I'm going to gather all the terms that are multiplying q of t, and I'm going to then look at the coefficient of those terms. So I'm going to have a dq dt is equal to something. Okay, so we can rearrange it to dq dt is equal to q of t times 1 over n of ty times partial derivative of m with respect to y minus partial derivative of n with respect to t. Now, if q is just a function of t, this object that multiplies q of t must also just be a function of t. And so that is the criterion for us to be able to find an integrating factor that's just a function of t. We have to have this object be just a function of t. But if that's true, then all we have to do is integrate that function and take the exponential of it. And we've solved the differential equation for q. Now, once again, I just want you to look at this. It looks like a very intimidating equation, but remember that 1 over n times dm dy minus dn dt, that's just some function of t. In this case, be a function of t prime that I have to integrate over. That's all. So it's really not something that you should really be intimidated by. And you have to recognize this is a special case. It doesn't work all the time. It's only in the special case where that object is just a function of t that I can do this. Okay? But when we do that, this will become the integrating factor. And then what I will find is I will multiply the q times the m, and I would multiply the q times the n. And then I have to find the f that will satisfy the exact derivative. Once I've found the f that satisfies that exact derivative, I just set it equal to a constant, and then the differential equation has been solved. So there's often a lot of algebra and other things that need to be done with this, but actually the solving of the differential equation part turns out to be very easy whenever you can express it in terms of an exact derivative. All right, so we've seen the one way of doing it when it's a factor of t. Let's take a look at how we do it when it's a factor of y. So in this case, dq dt is equal to 0, and my equation becomes q of y dn dt plus dq dy times m plus q dm dy. I'm going to do the same thing. I'm going to gather all the dq dy terms, put them on the left-hand side, and I'm going to then have everything else, which is multiplying q of y, appear on the right-hand side. So we're going to get dq dy equals minus q of y times 1 over m of ty dm dy minus dn dt. And what we need is that object that multiplies q of y to just be a function of y. If that holds, then we can solve for this particular integrating factor. So the requirement is that this object is just a function of y. And if that's true, then all we have to do is integrate it and take the exponential, and we get the integrating factor. Now, the only thing that you have to recognize that is the difference from what we did before is this exponential has a minus sign in the exponent, and it's a 1 over m rather than a 1 over n. So those are the two things that you have to remember in working out when the integrating factor is a factor of t or the integrating factor is a factor of a function of y. Okay, and then the same thing holds. Once I've got the integrating factor, I multiply the m and the n by that integrating factor. I then have to find the function for which the differential equation is an exact total derivative. I then set that function equal to a constant, and I've solved the differential equation. And it's that easy. Okay, now carrying it out, as I said before, it does require a lot of algebra. So let's take a look at an example. And the example we're going to try, this is closely related to a problem that you're going to have in the homework, but it is a little different. We're going to look at 3t squared y dt plus y squared minus t cubed dy is equal to 0. Let's take a look at those mixed derivatives for the m and the n. So first, we have to extract what the m and the n are. So m of ty is 3t squared y, n of ty is y squared minus t cubed. And now we can look at what is the partial derivative of m with respect to y, and is it equal to the partial derivative of n with respect to t? If it was, then this difference would equal 0. But we immediately see that the derivative of m with respect to y is 3t squared, and the derivative of n with respect to y is minus 3t squared. So they actually add together and they give me 6t squared. So they are not 0. So this is not an exact differential that I can work out. But if I take 6t squared, now you can take a look. If I took that and I divided it by n, that is not a function just of t, so that one isn't going to work. But if I divide it by m, the t squareds cancel, and you see that's just a function of y. So when I divide it by m, I do get something that's just a function of y, and now we can use our techniques to find the integrating factor. So minus 1 over m dm dy minus dn dt is equal to minus 2 over y. Now what do I have to do? I have to integrate that and take the exponential of it. So we're going to integrate it. and take the exponential, and we're going to find it becomes the exponential of minus 2 log y, which is just 1 over y squared. So that's the integrating factor. So I have to multiply the differential equation by 1 over y squared. That's going to modify the differential equation, but that modified differential equation is going to be an exact differential equation that I can immediately solve. So the differential equation is now going to become 3t squared over y dt plus 1 minus t cubed over y squared dy equals 0. And the claim is that this is an exact differential. So let's check it. The first thing we want to do is we want to take the partial derivative of our new m with respect to y and see is it equal to the partial derivative of the new n with respect to t. So we're going to be sort of working that out as we take a look at solving the differential equation. So df by dt is equal to 3t squared over y. If I integrate that with respect to t, I'm going to get t cubed over y plus some function of y. I also have to satisfy df by dy is equal to 1 minus t cubed over y squared. If I recognize that if I take the derivative of f with respect to y, I get a minus t cubed over y squared plus a derivative of h, I realize I have to have the derivative of h with respect to y equals 1, and that means h is just equal to y. And so I find f of ty is equal to y plus t cubed over y. So let's check. In order for this to be true, m must equal df by dt. So let's take the derivative of that with respect to t. I will get 3t squared over y. And you can immediately see m is equal to 3t squared over y. I need to have n equal to df dy. Well, df dy is equal to 1 minus t cubed over y squared. So indeed, n is equal to df dy. And that's how we make this thing into a total derivative. And that means that the solution comes from f equal to a constant. So if I let y0 denote y evaluated at t0, then all I have to do is set f equal to that constant value at y0, t0. And so y plus t cubed over y is equal to y0 plus t0 cubed over y0. I multiply that whole thing by y, bring everything to the left-hand side, I get a quadratic equation. Y squared minus y times y0 plus t0 cubed over y0 plus t cubed is equal to 0. Now I can just solve the quadratic equation. It's a little bit of algebra, but it's not too bad. I get 1/2 y0 plus t0 cubed over y0 plus or minus 1/2 the square root of y0 plus t0 cubed over y0 squared minus 4t cubed. And you see, I still have some choices here. There's a plus or minus sign that I have to figure out. And usually the way that this works is when we look at the initial condition, only one of those signs is going to actually give me the correct initial condition when t cubed is equal to t0. So the way in which you determine the sign is we set t equals t0, and if you look at expanding out that quadratic equation, you'll get y0 squared plus 2t0 cubed plus t0 to the 6th over y0 squared. And if I subtract 4t0 cubed, that becomes y0 minus t0 cubed over y0 quantity squared. I take the square root of that, I get y0 minus t0 cubed over y0. And now I have to worry about, it's really the absolute value of that. And what has to happen is I have to have the y0 terms, the plus or minus sign has to be chosen in such a way that the y0 terms add together, so I get y0 over 2 plus y0 over 2 equals y0. And the t0 cubed over y0 terms cancel because I'll have a t0 cubed over y0 minus a t0 cubed over y0. And in that situation, then I will have the solution that's equal to y0 at t equals t0, and that will be the correct root that I will have to pick. It all actually depends on the precise values of the y0 and the t0 in order for you to do that. And so I can't immediately tell you at this stage exactly which the plus or the minus sign is the correct result that you would pick for the actual solution of the differential equation. So I hope this discussion of integrating factors has helped you figure out what is a really difficult problem. And you're going to have some practice in working on these on the homework. And if you're running into any troubles with figuring out how it works, please come back and watch this video so that you can understand the details for how we solve these kinds of problems. And that's all that we have for this problem of the week.